Today we prove that every nilpotent operator has a basis made from Jordan chains. This is the part where Jordan form stops being a mysterious block diagram and starts being an actual theorem. Annoying, but useful. Let V be finite dimensional over F, and let N be a nilpotent operator on V. Nilpotent means some power of n equals 0. The operator keeps pushing vectors until eventually everything falls into the zero pit. We want vectors v1 through vk whose n chains form a basis of V. Each chain looks like V, nv, n squared v, and so on, until the next step becomes 0. A Jordan chain basis is just several such chains placed side by side. Revolutionary concept. Organized falling. In the reversed order, a chain looks like n to the av, then n to the a minus 1v, down to nv, then v. The operator n sends each vector to the previous one, and sends the first vector to 0. So the matrix of n on this chain has ones on the line above the diagonal and zeros everywhere else. Very neat. Suspiciously neat. Here is a typical nilpotent operator on F to the 5. One possible chain has length 3, and another has length 2. Together the chains give 5 basis vectors. The theorem says this kind of chain basis always exists. Not because matrices are being friendly, but because finite dimensional spaces eventually run out of room to misbehave. We prove the theorem by induction on the dimension of V. The smaller space will be R, the range of n. Because n maps its own range into itself, we can restrict n to R. And because n is nilpotent, it is not injective unless V is 0. So the range has smaller dimension. Finally, a strict decrease. The mathematician's favorite sedative. Apply the induction hypothesis to the nilpotent operator n restricted to R. So R has a basis made from chains starting at U1 through Uj. These are chains inside the range. The plan is to lift them one step backward into V. We also keep track of the chain ends. By induction, the last vectors in these chains form a basis of null n intersect R. That bookkeeping detail will prevent the proof from collapsing into hand-waving. The national sport of bad linear algebra explanations. Since each UR lies in the range of n, choose VR with NVR equal to UR. Then the chain in R gets lifted to a longer chain in V. Starting with VR and then continuing as UR, NUR, and so on. We have attached one new vector to the front of every chain in the range. It is like adding a prequel, except mathematically useful. The lifted chains account for the part of null n that lies inside the range. But null n might contain extra vectors not in the range. Choose a complement W so that null n is the direct sum of null n intersect R and W. A basis of W gives extra chains of length 1. Because n sends each Wi to 0 immediately. Short chains. The microwaved leftovers of Jordan theory. Now collect all lifted chains, plus the length 1 chains from W. Call this list B. We will prove B spans V and is linearly independent. Yes, both. Mathematics insists on receipts. Take any vector x in V. Then nx lies in R, so nx can be written as a linear combination of the chain basis of R. Because the range chains were lifted, we can choose y in the span of B so that ny equals nx. Then n of x minus y is 0, so x minus y lies in null n. But null n is the direct sum of null n intersect R and W. The null n intersect R part is spanned by the lifted chain ends, and W is spanned by the W vectors. So x minus y lies in the span of B. Since y also lies in the span of B, x lies in the span of B. Therefore B spans V. 1/2 of the basis proof has survived contact with reality. Now suppose a linear combination of all vectors in B equals 0. Apply n to this relation. The W vectors disappear because they are in null n. After applying n, every non-final coefficient becomes a coefficient in the chain basis of R. Since that chain basis of R is linearly independent, all those coefficients must be 0. Only the coefficients of the lifted chain ends, and the coefficients of the W vectors can remain. The remaining relation lives inside null n. The lifted chain ends form a basis of null n intersect R, while the W vectors form a basis of the complement W. Because the sum is direct, the only relation among these two groups is the trivial one. Thus every coefficient is 0. So B is linearly independent. We have proved that B spans V and is linearly independent. Therefore B is a Jordan chain basis for the nilpotent operator n. The theorem is proved, despite notation trying its best to look like a plumbing diagram. For the matrix, reverse each chain, n to the AV first, then n to the A minus 1V, down to V. In that order, n sends each vector to the previous basis vector and sends the first vector to 0. So each chain contributes a nilpotent Jordan block. Zeros on the diagonal, ones directly above the diagonal, and zeros elsewhere. A nilpotent operator is therefore a direct pile of these chain blocks. At last, the blocks are not decoration. They are the proof-wearing pixels. The final result is simple. Every nilpotent operator has a Jordan chain basis. Hence a block diagonal matrix made of nilpotent Jordan blocks. Next, on a generalized eigenspace, T equals lambda I plus a nilpotent operator. So the same chains become Jordan blocks with lambda on the diagonal. Humanity survives another matrix theorem.